Okay, thank you. So first of all, thanks to Anston for organizing this workshop. So in this talk, I will survey some use of inductive definitions in constructive mathematics, and I will talk about generalized inductive definitions. So, and I will try to connect some of the examples with what Laura presented yesterday and what Mark talked about. Main example actually will be Cantor-Bell-Dixon as analyzed by Lorentzon, because historically it was an important example for the discussions on whether or not generalized inductive definitions are predicative or not. And I will try to end, if I have time, with some remarks on invariance. So first of all, so generalized inductive definitions in mathematics. So I think one first example is ordinals, and Cantor introduced ordinal for iterating the process of taking accumulation points in a set. And so that's this operation of a derived subset of F. So the set of accumulation point of F, and if F is closed, F prime is a subset of F. And then it's natural to iterate this process, first finitely, and then if it doesn't stop after a finite number of time, you get a decreasing sequence of closed subset, non-empty closed subset, and you can take the intersection, countable intersection. And Cantor introduced a symbol for representing this. It was omega, and that was the birth of ordinals. And this operation, so it's important for a process which is Cantor-Bell-Dixon. So it will stop these operations. You can iterate it over ordinals, and it will stop for if F is a closed subset of real numbers. It will stop after alpha, where alpha is a second countable ordinals. And there it's, when it stops, it's either empty or perfect. So if it's empty, then F was countable. If it's a perfect subset, then F has the power of 2 to the Aleph 0. So for Cantor, it was this process was important to prove a special case of continuum hypothesis for closed subsets. So that's one example in mathematics, and another example that we will also discuss in the setting of constructive mathematics is Borel's introduction of Borel sets, okay, where you iterate the process of disjunct union and subtraction, starting from open intervals. So inductive definition in logic. So I mean, so two references are Frege Begriffsschrift, where Frege defines the transitive closure of relations, and this is defined using impredicative quantification. In Principia Mathematica, this was generalized to transfinite induction process. So there is a treatment of transfinite induction in Principia Mathematica, also with impredicative quantification. So inductive definition in constructive settings. So two important references. So I will mainly consider inductive definition in type theory, and two important references are so the one that Peter gave yesterday, so on theory of inductive definitions, and another one that I find really very, very clear. And so this is on the strengths of intuitionistic reasoning. So it's a preprint that was not published because the system used the type of all types that was shown inconsistent by Girard. But most of the examples that Martin Love present in this preprint can be read in a system with a hierarchy of universes. So so there are really nice sentences in this in this preprint, like describing in a very relevant way what is type theory. So type theory is a system where you can represent abstract entities represented by certain symbol configurations and definitional schema. So and type theory is a framework where you can express conceptual mathematics in a computational way. And what is interesting is that all computations are expressed in a fixed programming language, actually. When you analyze what are the programs that represent these abstract entities, it's a fixed functional programming language with a general recursion and case analysis. So I think even the example that Peter presented yesterday with very complicated inductive definitions can be represented in this language since it was represented in Agda. So the examples that Per gives are examples that we saw yesterday. So I will go very quickly through it. So type of natural number with constructor 0 and successor. And then you can define, you have the elimination schema, so which represent both primitive, so recursion and primitive recursion and proof by recursion on natural number. That's what the comment of Martin Loff in this paper about this fact. And then in this preprint, he also presents the type of ordinals where you have not only 0 and successor as constructor, but you have also limit operations. So if you have U is a function from NAT to ORD, then limit of U is an object of type ORD as well. And then you have the principle of recursion on this type, so which is given in this way. So, but we saw this yesterday, so I will not spend time on this. And this represents as well the principle of recursion and how to prove principle of transfinite induction over second number class ordinal. So now a remark of Kreisel that okay, I found so by the practice of constructive mathematics. So I was aware of this fact because I noticed that actually most proofs that are presented classically are actually presented in a more elegant way and more to the point way when you present things in a constructive setting, intuitive setting. And of course, I mean, this was already known and emphasized by Kreisel. So who says, so this theory, so the theory of ordinals is much more elegant if done intuitionistically. And so I will try to present a small example of this. And that this example is a slow growing versus fast growing hierarchy. So first, I mean, as presented by Hardy, so that's this idea. So yes, maybe I should say, so the goal of Hardy in this paper, that was very influential because it, I mean, Veblen was referring to this paper as well. So the goal was to show very concretely that Aleph1 is less than 2 to the Aleph0. And so the way to do it is to produce Aleph1 elements in 2 to the Aleph0. And 2 to the Aleph0 is the cardinal of functions from NAT to NAT. So the goal of Hardy was to exhibit Aleph1 functions from NAT to NAT. And his idea was the following. So it was a table. So you start with enumeration of natural number. At successor stage, you shift the sequence. So you start with 0, 1, 2, and then first stage you have 1, 2, 3, second stage 2, 3, 4, and so on. And in this way, you have a list of functions from NAT to NAT. And then for the limit case, so for omega, you reach a limit ordinal, you diagonalize this table. So for omega, you will diagonalize. So you have 0, 2, 4, 6, and so on. So you get even number. Omega plus 1, so you shift the sequence, and so on. And in this way, you associate to ordinals of second class functions. And the goal of Hardy in this paper was to show that all these functions are different. So they are Aleph1 function in this way. So this is what is called now so Hardy hierarchy of functions. And the slow growing hierarchy, so it's a variation of this, but you instead, so you start with a constant sequence, 0, 0, 0. And then at the successor stage, you add 1 to this sequence. So 1, 1, 1, 1, 1, and so on. and then 2.2. And at limit case, you take the diagonal as well. So at the limit case, you will get 0, 1, 2, 3, 4, 5, 6, 7, and so on. So and this is also you can prove that all functions that you get in this way are distinct. So that's injective enumeration of functions. And the goal is to see if there's two hierarchy can coincide. So first hierarchy is called H. The second is called S. And the problem is, can we find alpha such that a given alpha, can we find beta such that H of alpha is equal to S of beta? And another problem is, can we find alpha so that H of alpha is equal to S of alpha? Okay, and Stan Wenner, so conjecture that this holds actually for alpha is gamma 0, so Pfefferman ordinal. But actually, this is not the case. And so this is the representation of Hardy hierarchy in so type theory extended with a type of ordinals. So H takes ordinal, a natural number, and gives a natural number. So H of alpha is a function from nat to nat. And the slow growing hierarchy, so S of alpha will be a function from nat to nat. Okay, and that's so it's very simple to represent this in type theory with inductive definitions. And so they don't coincide for alpha, beta, gamma 0. So actually, so Jean-Yves Girard showed that we have to go much further. So if you look at H of epsilon 0, so this is equal to a slow growing hierarchy, but you have to go much further. So you have to go up to Howard ordinal. And the first place where they coincide is actually the ordinal of ID less than omega. So it's a very high ordinal. And so it's interesting, relevant to present this example because you have an example of an ordinal of second number class, so Howard ordinal, which is defined using so big omega, which is actually of the third number class. So this is an example of a collection which is not stable. So the collection, if you consider type theory with only ordinal of second number class, you can define ordinals, but you will not be able to define the Howard ordinal. And you will be able to define it if you add a next level ordinal, so ordinal 2, where you can, you have for constructor, so 0, successor, limit, countable limit, and uncountable limit. Formally, there is no problem to add this to type theory. But when you do this, I mean, that's an example of a non-stable collection. So NAT is unchanged when you add this new type, but the type of ordinal will be changed. You can, yeah. So that's an example illustrating, I mean, what Laura was presenting yesterday, of something which is not stable by extension. Okay. Yep. So it has some flavor of impredicativity. Yeah, exactly. So that's, I mean, this needs to be actually analyzed further. Yes, exactly. So, I mean, iteration of inductive definitions, formally, it's very simple to do. I mean, it's only you add more constructor and enumerations over types that you have already defined. And this was so as non-fundamental inductive definitions for what terminology of instance. So this was already in Lorentzon's work. So Lorentzon's could iterate predicate in this way. As a data type, so this was suggested in Tate's paper, constructive reasoning. This was used in Scott's paper on constructive validity. So that's a type of tree, which so you have a constructor 0 and then a constructor. So for any enumerations over a type, an arbitrary type X, you have a type of tree like this. And this was generalized much further by Martin with a W type. Okay, so you can play, you can use this, and then you can define things in type theory with using this new data type. And it's then, I mean, I won't go over the definitions. I mean, it's only that it's very simple to do it in type theory. very simple to define the proposition by recursions or as an inductive family, so inductively defined predicate. And then it's very simple also, as Kreisel said. So the paper of Stan Wenner, so where he presents Girard's result, was done in a classical meta theory, but actually you can follow this paper and prove what he was proving. So this theorem that says that a slow growing hierarchy, so S of something, is equal to the Hardy hierarchy. You can do it, and you can follow the paper as well. And this was one of the first example actually we tried in implementation of inductive types. So that was this example. And this is an example of ID2 once more. And you have, when you do this proof, so like Howard ordinal, you define an ordinal using ordinal of third class. So it's a seemingly impredicative definition. Or if you want another way to say it, is that it's, yeah, well, better say only this, that it's seemingly impredicative. Okay. So that was the first example in constructive mathematics, so ordinals. Second example will be how to analyze topology. So actually, that was the motivations of Brouwer, actually, for inductive definitions. It was analysis of real numbers and Baire space. As noticed by Tate in this paper, very important paper, I mean, constructive reasoning, I think from 67. So Brouwer applied the theory of ordinals for analyzing Baire space, but actually it's just as convenient to work directly with trees. So it's, we don't really need ordinals for doing this. If we have a system with inductive definitions, and we can use tree instead. This was also done by, but informally, by Lorentzen in this also very important paper, so logical reflection and formalism. He calls this a critical analysis of topology. So it's a non-naive analysis of spaces where a space is not seen as a collection of points, but in a more refined way. And he has an example that we will go through, so analysis of Cantor-Bendixson actually, in this paper of logical reflection and formalism. And this is beautifully presented in the book of Martin Love, so Notes on Constructive Mathematics. So this book is written in the setting of recursive mathematics, but actually most of the results hold in constructive mathematics. So you can read the book having in mind type theory with inductive definitions. So Cantor space, let us look at analysis of Cantor space first. So as a set of points, so Cantor space is a set of infinite binary sequences. But then how to do a critical analysis of Cantor space? So what is an open of Cantor space, open subset of Cantor space in a non-naive analysis of Cantor space? An open subset of Cantor space is actually determined by a subset of basic open, and the basic open is a finite binary sequence. So we think of a finite binary sequence as a closed open subset of Cantor space. So there's a set of all infinite sequences that extend this finite sequence. And then we can define the covering relations by inductive definitions. So when is a finite sequence sigma covered by U? So it is covered by U if it is in U, or if sigma 0 and sigma 1 are covered by U. And that's the definition that you find in Notes on Constructive Mathematics. And then you have the notion of bar. So U is a bar. So U is a covering of the space if U bar the empty sequence. And the closed open subsets of Cantor space form a Boolean algebra, propositional logic, so built from these atoms, starting from these atoms. So from a point of view of constructive mathematics, Cantor space is actually another way to talk about this Boolean algebra, or to talk about this relation. And the proof of to be a bar is a finite object. So with this analysis, so Heine Borel is completely trivial. So if U is a covering, it will be this will be witnessed by a finite tree. So it holds already with using a finite number of elements of U. Okay, so that's a proof that you find in knots of constructive mathematics. Okay. And for bare space, there we have a generalized inductive definitions. So the definition of being a bar now is this infinitary definition. So now you have a tree. The proof of U bar sigma is a tree, but which may be countably branching. So that was the use of generalized inductive definition in constructive mathematics. But in another use, which is different, so is in the work of Novikov and Lorentzon. And this was independent, actually. And this was a new use of generalized inductive definition. And for Lorentzon, this was a purely algebraic problem. So it was how to build the free sigma complete Boolean algebra on a given Boolean algebra. And for doing this, generalized inductive definitions are used twice. So first, it's used for what are the elements of this sigma complete Boolean algebra. So there will be infinitary expressions where you iterate countable sup and countable minima. And for defining the order relations between those infinitary symbols, this also is inductive definition. So this is defined inductively with a generalized inductive definition. So there you have a fundamental inductive definitions. Here you have a non-fundamental inductive definitions. The terminology of Kim. And using this technique, you can prove this fundamental result that the map from B to the sigma completion is an embedding. And Lorentzon noticed that the proof of this fact is formally similar to the original, so unpublished proof of consistency by Genson using omega rule. And this was really surprising for Lorentzon that he was doing this he was doing lattice theory. And then at some point he remembered that he has seen a talk of Genson. And what Genson was doing in this talk was really formally similar to what he was doing in a purely algebraic way. And so there, the goal of Genson, as he formulated, was to explain in a constructive way the classical notion of truth of an arithmetical statement. And this cannot be Tarski truth semantics, because for a statement like this, so this statement is that any function has a minimum. It's classically valid, but given f, you cannot find the n as a recursive function of f. So you need something more subtle in order to explain what a classical mathematician thinks when he thinks that this formula is valid. And that was what Genson was doing, and that's analyzed by this generalized inductive definition. So this was done by Lorentzon, as I said, so published in 51. But Martin Love, so in Notes on Constructive Mathematics, go further than this. So Martin Love used exactly the same construction as Lorentzon, but he noticed that this B tilde, so the sigma completion of B, if you start from the Boolean algebra of closed open subset of Cantor space, what you get is exactly the sigma complete Boolean algebra of Borel subsets of Cantor space. So you have a presentation in constructive mathematics of the notion of Borel sets. And that's quite remarkable, actually, that you can do it. And this provides a constructive way to understand inclusions between Borel's subset of Cantor space. So you can do something similar, starting from the Boolean algebra with only two elements, 0 and 1. And so Martin Love, so not in notes on constructive mathematics, but in talks, he suggested that this notion of hyperarithmetical proposition that was mentioned in the talk of Laura, so can be defined in these constructive settings as an element of the sigma completion of the trivial Boolean algebra. The Boolean algebra 0, 1. So you get a representation of hyperarithmetical proposition. So we have covered two examples of that was actually first example in classical mathematics of use of generalized inductive definitions. So example of ordinals and example of Borel sets. So in this approach, so that's this point-free approach, so both the basic open sets and the Borel sets are seen, so not as set of points, but as purely symbolic expressions. So for instance, if you want to look at the branch, so with only 0, 0, 0, so this sequence, so the singleton having only this sequence is a closed subset of Cantor space. So it's a Borel subset of Cantor space. Formally, it will be represented by this formula, infinitary formula. So you say that for all n, alpha n is equal to 0. A more interesting example, so the set of normal sequences. So sequences that such that the probability of having a 0 or a 1 is 1 over 2. So that's a normal, called the normal sequence. So it can be represented as a Borel set, and a Borel subset of Cantor space, and this is represented by this a formula of this form. So yeah. So you get a representation of Borel subsets. So Martin Love suggested to define the hyperarithmetical real to be a Dedekind cut, which is seen as a family of hyperarithmetical propositions over operation. And following so problem in Lusin's book, he formulated the problem of defining the measure of a Borel set as a hyperarithmetical real in a purely inductive way. So it's a very natural problem. So Borel sets are defined inductively. And if you look at the definition of measure as done by Lebesgue, this definition was impredicative. So the problem is, can we have a purely inductive definition of the measure? So this definition should be done by induction on the structure of the Borel set. So what I noticed is that actually we can use an insight of Ries in this paper. And so it's not possible to define directly this as a function of this, so by induction on the Borel set. What is possible to define inductively is this function that to a basic open subset associate the measure of X intersection P. So this function can be defined by induction on X. So using this insight, so which is due to Ries, so it is possible actually to define in a purely inductive way with a generalized inductive definition the measure of a Borel set as a hyperarithmetical function. So I presented this more in detail in a paper on Lorentson and constructive mathematics. So for instance, the measure of the set of normal binary sequence can be shown to be of measure 1, so in this way, with a purely inductive proof. So in this paper, I present also the really fundamental work of Lorentson, which is an analysis of Cantor-Bendixson. So we saw Cantor-Bendixson. So it was really at the origin of definition of ordinals. And there was a problem of can we represent this analysis, which can be done impredicatively or by iteration of ordinals. But this definition looks very classical. Can we do it in a purely inductive way? And this was solved by Lorentson in this paper that I mentioned already. So what is the problem? The problem is given a closed subset Cantor space, can we define what we obtain by iterating this process of taking the accumulation points, okay, so which is called the perfect subset of this set. Okay. So that's so this is the definition in classical mathematics where we iterate this process through all ordinals of second normal class, but we need really a classical meta theory for presenting this. Can we do this in a purely inductive way? And the fundamental insight of Lorentson was to see that, so if we look at the, instead of talking about closed subset, but open subset of Cantor space, and we saw how to deal with open subset of Cantor space. So can we define the open subset associated to K given the open subset associated to A? And Lorentson was able to do this. And what is very interesting is that when you do this, so if you start with an open set given by a predicate on finite sequence, you get a predicate, a new predicate, which corresponds to this open subset of the complement of K. But V is obtained from you by a generalized inductive definition. You cannot do it with a finitary inductive definition. And why it was so it was very important for Kreisel because Kreisel had shown actually that V, so the perfect closed subset, cannot be defined in a predicative way from you. He has, as Laura mentioned yesterday, so Kreisel had the analysis of predicativity in the 50s. And according to this analysis, so V, actually it's impossible to define V from U in a predicative way. So it was very surprising for Kreisel that Lorentson could do this definition. And, but for Kreisel, this definition was non-predicative. So it was constructive, but in a generalized meaning of constructive. So I will, yes. So, I mean, so I've not yet understood his notion in a classical way. I mean, all his papers are done in a classical meta theory, but I have this conjecture of what it should be in a constructive way. And I think, so constructive, predicative, there will mean that it can be represented by a hyperarithmetic proposition. So it should be, so a predicative subset of NAT should be given by a family of hyperarithmetical propositions, where I've defined hyperarithmetical as this sigma completion of 0, 1. Okay. So I think this corresponds. My conjecture is that this is a way in type theory to talk about hyperarithmetic. But this needs further, actually, to be analyzed further. So you need ID1. So that's, yeah. So you need you don't need the W, but you need a generalized inductive definition. But not crucially only ID1 and not ID2. So and the conjecture is that you can represent Kreisel's result in setting of type theory, so that giving an example where U is decidable and V is not hyperarithmetic. You need to define the V, you need ID2. And so historically, so this shows the relevance of generalized inductive definition for constructive mathematics. And this is stressed very strongly in the paper of Lorentzon and Myhill. So this paper, constructive definition of certain analytic sets of numbers. And in this paper, so in a provocative way, actually, Lorentzon called a definition that can be done with generalized inductive definitions predicative. And Kreisel actually later he objects to this use of predicative for this notion because of this example of actually Cantor-Bendixson. Yes. So I want now to present another example of a property of Cantor space. So this was actually a property of Cantor space. So how to define this Cantor-Bendixson process on the closed subset of Cantor space. And this is a property of Cantor space which requires also a generalized inductive definition. And this is the principle of open induction. So in terms of points, so this is the following principle. So this principle. So I will first motivate this principle by the following remark. So if we look at the lexicographic ordering of finite or infinite sequences, binary sequences, this is not a well-founded ordering. So for instance, you have so 1 is strictly bigger than 0, 1 for the lexicographic ordering, which is strictly bigger than 0, 0, 1, and so on. So you have an infinite decreasing sequence. So this is not well-founded. So another way to express that this is not well-founded is that the principle of well-founded induction doesn't hold for infinite sequences of on Cantor space. But it holds. So if you restrict yourself to properties that are open. So if U is an open subset of Cantor space, so this is the principle of, the premise of the principle of well-founded induction. If U is an arbitrary property, and as we saw, it doesn't hold. But if U is open, it holds. So if U is an open subset of Cantor space, if you have this property, then actually U is a covers Cantor space. So this is, and another form of this open induction is on real numbers. So it's the same. So the ordering on 0, 1, this ordering is not well-founded for real numbers. But so the principle of induction is not valid. But actually, it is valid if you consider properties that are open. And this principle is, so classically, the way to prove this is as follows. So these implications hold for x is 0, because there is nothing less than 0. So you get that 0 is in the interval U. And since U is open, so you have a number strictly bigger than 0, which is in U. And so you call this number A1, X1. X1 is in U, U is open, so you have X2 strictly bigger than X1, which is in U. And you can keep doing this. And you can keep doing this omega times. And if you take the limit, so X omega, you can prove it will still be in U because all numbers below X omega are in U. Okay, but X omega may be strictly less than 1. So, but X omega is in U, U is open, so you have X omega plus 1 in U as well. And you can keep doing this. And the process, so classically, the process stops before you reach, you exhaust all second number class ordinals. Okay, so that's a classical way of proving this open induction. So what I want to present now is a critical analysis of this principle. So let us look at this in a point-free way. So let us look at this premise, this property of alpha in a point-free way. So, so it says that whenever beta is lexicographic less than alpha, then beta is mu. So actually, it means, so I will not go in details, but you can show that it means exactly that alpha is in the subtree determined by this predicate. And sigma this way. When you look at this from a point-free way, you get that the premise, this premise star, says that U is not may not be a bar on all Cantor space, but U is a bar on this this subtree. So and once you have this analysis, so it's a direct proof by induction that if U is a bar on this subtree N, then U is a bar. So the point-free analysis of this principle becomes a simple inductive proof by induction. But the point is that since M refers to a notion of bar, so this notion of being a bar on this subtree is now a generalized inductive definition. So in order to prove this principle of open induction, you need a generalized inductive proof. So, and this has been analyzed by Wim Wellman in the setting of intuitionistic mathematics. So, so you have a setting where you can have a Fan theorem or a bar theorem, and Wim Wellman proves that so in the basic setting of intuitionistic mathematics, so without the Fan theorem or bar theorem, this principle of open induction that you can formulate as a property of Cantor space implies that epsilon zero is well founded. So from this principle, you can prove that epsilon zero is well founded. And then using a previous result of Troelstra, that so the result of Troelstra was that if you have only the Fan theorem, you cannot show that epsilon zero is well founded. Because if you have so what Troelstra proved was that basic intuitionistic mathematics plus Fan theorem is conservative over Heyting arithmetic. So you cannot prove epsilon zero well founded there. So from this, it follows that using only Fan theorem, you cannot prove this principle of open induction. So that's so you need bar theorem, or you need something stronger than the Fan theorem to prove this principle. So I conjecture that there is something similar for bare space. So if you formulate open induction not over Cantor space but over bare space, so now you have all infinite sequence of natural number. The conjecture is that this cannot be proved in the system of Kleene and Vesely that have bar theorem. So the strength of this system is ID1, and the conjecture is that this principle of open induction over bare space cannot be proved in ID1. So I have no idea how to prove this, but it's very likely because when you see how to prove it, it looks like you need a generalized inductive definition in ID2. Okay. So it's interesting that this requires ID2. And but also what is interesting, so from my experience in practice of constructive mathematics, is that it's very seldom that you need more than ID1 when doing mathematics. Okay, when doing examples in so basic example in mathematics. So ID. And it's so there are few examples which requires ID2. And I think the example also requires more conceptual analysis. Actually. On the other hand, so following Kreisel, So despite the fact that Kreisel was objecting to about calling ID1 predicative, I mean, for him, he was calling this constructive. And then Kreisel started a program of iterating inductive definitions for proof theory and for showing consistency proof of subsystem of analysis. Okay, so it was started in the 60s with Tate, Howard, and then Buchholz, Sig, Wilfried Sig, Pfefferman. So that was a very successful program. But this requires going much further than ID1. I think this step from ID1 to ID2 has been analyzed too little, so in a conceptual way, but it's very difficult actually to do this. So, for instance, Tate in this paper that I've cited several times states that so I have been unable to arrive at any conception of inductive definitions which distinguishes the countable case from the more general case. So for Tate, so as soon as you accept ID1, you should accept ID2, ID3, and so on as well. So W type and so on. So I want to end by a short comment on this issue. This is so connected to Laura, so invariance. I mean, discussion on invariance. So how to represent mathematically the notion of growing collection. So we saw actually one example of this with so the Howard ordinal. That was an ordinal of second number class. But this ordinal, it will not be possible to define if you have type theory with only ordinal as a data type. Okay? So you need to go further. So that's an example of something which is not stable by extension. So that's one notion of extension. So when you add new data types. So and an example was also in Peter's talk. So when you have this Malo universe, I mean, you should be able to prove much more statement and define much more ordinals also already in the type OR when you do this. So whenever you add new data types, new universes, some types gets bigger. So there is other notion of extension, which is extension by shift models. So this was, for instance, emphasized by Dana Scott. So what is a real number in shift models over 0, 1 or over a topological space? So it will be a function. You can see it as a function on the space to real number. So real value function on this space. So you see intuitively that when you do that, you add new real numbers. So for instance, I mean, so intuitively, the real number in the starting model are only the constant, correspond to the constant functions from 0, 1 to R. But when you go to these shift models, of course, you get new functions. For instance, the injections 0, 1 to R is not constant. So it's a new real that you get by shift. So this is another way to understand how collections are not stable by change of base. A set of functions or a set of real numbers may grow by shift extensions. And then you have to be very careful when it becomes bigger, because when it becomes bigger, so when you quantify your functions, since you have more functions, so you can have a statement that was valid in the base model that becomes not valid because you get the quantification is stronger. So this statement, for instance, it goes in the negative way. So if it may be true in the base model and may not be true in the extended model. So this means you should not use in constructive mathematics. You should not use this as a definition of covering or definition of bar, because it will not be stable by extension. But the statement, the definition with a bar, okay, is stable by extension because it's an existential statement on well-founded trees. So if it is valid in the best model, it will be valid in the expanded model. So that's remark on invariance. So some types are stable by Schiff extensions. So the types of natural number or finite type, it stays the same. There is no new numbers when you go to a Schiff model. Some types may grow, so type of functions, type of ordinals, so you get more ordinals. Type of bars, you get more bar, but it grows. But some types have a very complex behavior. So if you iterate function types or these types of ordinal of third class, it's not clear at all what happens when you do these extensions. And ID2 as well. So so technically, and to connect it with the talk of Mark yesterday, so I mean, coherent theories that Mark mentions have this property of being preserved by extension, Schiff extension. So this has been noticed in categorical logic. So to conclude this talk, so generalized inductive definitions, so seem essential to represent in a constructive setting some notions and results of classical mathematics. So we saw, I mean, example from Genson, Novikov, and Lorenzen. If we want to understand what classical mathematicians means by a validity of an arithmetical statement, we need a generalized inductive definition. If we want to understand the inclusion of Borel subsets, what classical mathematicians means when he says that two Borel subsets, one is a subset of the other, we also need a generalized inductive definition. If we want to understand Cantor-Bendixson from a constructive point of view, we need generalized inductive definitions, and it cannot be understood in a predicative setting according to Kreisel definition of predicative in the 50s. And so that was list of examples where you need generalized inductive definitions. And second, what I wanted also to say in this talk that I think we need conceptual analysis of what happens when you extend generalized inductive definitions besides ID1, so ID2 and ID3. I think it needs further analysis, and I will stop here. Yes, thank you.